Okay, is my screen is visible? Yeah. Okay. Yes. Okay. My screen is visible, no? So, in the last class, we seen about the CMOS voltage transfer characteristics. Okay. In that, we already seen the CMOS voltage transfer characteristic. Today, we are going to discuss about this CMOS noise margin and how to calculate VIL, VIH also. We'll see. Okay. So, so, um, so CMOS noise margin, and we are going to calculate this VIH and VIL. Okay, VIH and VIL. Okay, so VIH and VIL. uh, so we already seen the CMOS CMOS circuit. So here this is VDD, and here you have uh, PMOS as pull up and NMOS as pull down, no? So this is PMOS as pull up, and NMOS as pull down, and MOS as pull down, and this is a ground. Okay, so ground, and this is V in. Okay, and this is V out. Okay, and we already seen what is this. So this is a gate, source, drain, and gate, and this is source. Okay, so this one, what is this one? This is VG. So this is PMOS, and this is what? NMOS. Okay, NMOS. Okay, and next VGSN. What is this? This is VGSN, and this one is VGSP. Okay, and next this one is what? VDSP, and this one is VDSN. Okay, so we already came across what is this this VGSN and all those things. What is what is VGSN? VGSN, that is equal to what? V in. Okay, we already seen in the last class. VDSN equal to what? V out. And this is for NMOS, and for PMOS this is for NMOS. Okay, for PMOS. Okay, for PMOS VGSP equal to what? VGSP equal to V in minus VDD, and VDSP equal to what? You got V out minus VDD. Okay, this we already seen in the last class. Okay, so this I am going to use, that's why I am writing. Okay, I am going to use in the equation. Okay, and next, if you draw the characteristics. Okay, characteristics of this voltage transfer characteristics. If you see the voltage transfer characteristics, I'll draw the voltage transfer characteristics. Okay, my voice is audible, no? It's everything fine. Shall I move forward?
Yes, sir.
Yes, sir.
Okay. Next, you see. So here this one is something but V out, and this one is nothing but V in. Okay, and you have like curve will be like this. So here you will get what? It will start from VDD. Okay, so this is VDD, and it will come like this, and here what will be there? So so here if you see, so this one, this let us take this point. Okay, this point. Okay, this point is a dV out by dV in, that is equal to what? -1. This slope equal to what? 1, -1. Okay, this slope equal to -1. In this, NMOS will be operated at saturation region, and PMOS will be operated at linear region. Okay, in this point. Okay, and next so this point I can consider this point. Okay, this point is nothing but what, so let us take this is 0 only. This is what VIL, input low voltage. Okay, input low voltage, and this point is VDD by 2, VDD by 2, and this slope is there, no? So this slope, if you consider this slope, so this slope, what is this slope? This is dV out by dV in, dV in, that is equal to -1. In this situation, NMOS will be in linear region and PMOS will be in saturation region. Okay, PMOS will be in saturation region. So here this is VDD only, maximum value VDD, and this point is nothing but what, VIH. Okay, VIH, and this is VIL. Okay, I want to calculate VIH and VIL, and from this I want to calculate the noise margin. Okay, so noise margin, that is nothing but NML. Okay, and NMH. Okay, NML and NMH I need to calculate. Okay, so anyway, for CMOS circuit, what is VOH? VOH, that is equal to VDD. VOH equal to what? VDD, and output high value, that is VDD, and output low value VOL. VOL equal to 0 also. Okay, VOL equal to this 0 also only, but if I want to calculate this, I need to do some derivation. Okay, so we'll see the calculation of VIL and VIH. Okay, so if you see the calculation of VIL and VIH, so we'll see here. So what is VIL, calculation of VIL? Okay, so VIL calculation. So if you see the VIL calculation, that point, what is that point for VIL calculation? You already seen that point. Okay, this point, dV out by dV in equal to -1. NMOS will be saturation and PMOS will be linear region. No? So that point I am writing. Okay, VIL calculation. So so in this situation, this dV out by dV in, that is equal to what? -1. In this, NMOS will be what? Saturation. NMOS will be saturation, and PMOS will be linear. Okay, PMOS will be linear. Okay, in this condition, I can say that both currents are same. ID and SAT equal to what? ID and linear. ID and linear. Okay, so ID, drain current in saturation equal to drain current in linear region. So so what I can write? So ID and saturation, that is equal to ID and linear region. ID and linear region. Okay, so I am writing the current equation. This is what, Kn by 2 in saturation region. Okay, so VGSN minus VTN whole square, that is equal to I am writing this one in linear region. Okay, IDP. Okay, IDP linear. This is IDP linear. Okay, PMOS is in linear region. No, so this is the Kp by 2. Okay, so K equal to what? We already seen in the drain current equation, mu n COX W by L, that I considered as K constant. Okay, mu n COX, mu n is nothing but mobility. Okay, this is for NMOS, and for PMOS this is Kp. Okay, and Kn equal to what? Mu P COX W by L. Mu P COX W by L. Okay, so this is for PMOS. Okay, Kp into 2 into VGSP minus VTP into VDSP minus VDSP whole square divided by 2. Okay, so so here next I need to substitute. Okay, okay, so we already seen, so that means VGSN equal to what? So we already seen, no? So I'm writing with other color. VGSN. Okay. So if you see the VGSN, VGSN equal to what? Vin. Okay. And VDSN equal to what? Vout. And VGSP equal to what? We already got VGSP equal to what? Vin minus VDD. And VDSP equal to what? Vout minus VDD. Vout minus VDD. Previously, just whatever from the CMOS circuit, I am using this. See here. So VGSN equal to Vin, VDSN equal to Vout, and VGSP equal to Vin minus VDD, and VDSP equal to Vout minus VDD. Okay. So that I am going to substitute in this above equation. Okay. So I am going to substitute in this above equation. So if I substitute, what I will get? See here. So I will substitute here. So Kn by 2, and what is VGSN? Vin minus VTP whole square, that is equal to Kp by 2, 2 into VGSP. What is VGSP? Vin minus VDD, minus VTP into VDSP. So VDSP is nothing but Vout minus VDD, minus VDSP whole square. So Vout minus VDD whole square. I think divided by 2 will be not there. Here 2 is there. No, here divided by 2 is not there. Okay. So here anyway you multiplied with 2. Okay. 1 second. So this is not there. Yes. So this is the value. Okay. So next, so I need to differentiate the above equation with respect to what? With respect to Vn. Okay. So with respect to Vn, I am differentiating the above equation. Okay. So when I am differentiating, okay, differentiate the above equation with respect to what? With respect to Vn. Okay. When you differentiate, what you are getting? So here this is what? Kn by 2. Differentiation of x square. What? 2x, no? So 2 into Vn minus VTP, that is equal to Kp by 2. So differentiation of what? UV formula. Okay, I need to apply UV formula. Okay, so this is U and this is V. Okay, so what is the differentiation of UV formula? U into dV by dx plus V into du by dx, no? That I am applying. Okay, so that means U means what? 2 into Vn minus VDD minus VTP. This is dV out by dV in. Okay, dV in. Next plus what you will get? V out minus VDD into remaining all are constant only. You will get 2 here. Okay. So V in by dV in by dV in equal to 1, no? So you are getting 2 here. Okay, you are getting 2 here. And next minus 2 into V out minus VDD. Okay, differentiation of x square is what? 2x, no? So dV out by dV in. Okay, dV out by dV in. Okay, and next what I will do? Next here so anyway 2 get cancelled, no? This 2 get cancelled, this 2. Okay, all 2 get cancelled. Okay, so what I am getting? This equation, if you rewrite this equation, what I am getting? See here. So I want to rewrite this equation. Okay, so Kn into Vn minus VTP, that is equal to Kp into Vn minus VDD minus VTP into dV out by dV in. Okay, dV in plus V out minus VDD minus 2 V out minus VDD into dV out by dV in. Okay, dv out by dv in. Okay, so next what I am doing, I am bringing this vtn this side. Okay, so v in minus vtn. Okay, so v in, okay, so here I am taking common v in common. Okay, so this v in I am bringing to one side. So what happens here, it will come minus v in, you will get no minus. So next what I am doing means I am substituting dv out by dv in equal to what, minus 1, no? So when I substitute, what I will get, so kn into v in minus vtp, that is equal to kp into, so if I substitute and write, what I will get, minus v in plus vdd. Okay, so this dv out by dv in I am substituting as what, minus 1. Okay, so when I am substituting, what I am getting, plus vtp. Okay, plus vtp plus v out minus vdd, minus vdd. Okay, anyway 2 get cancelled now, so 2 will be not there. Plus v out, not plus plus v out, so minus into minus plus, this is minus 1, plus v out, again minus into minus plus, so plus into minus means minus vdd, minus vdd. Okay, and next what I am doing, so I am bringing this kp, kn and kp on one side, so this one on one side, so this is what I will get, kn plus v input I am taking common, kn plus kp, that is equal to, so here plus kn into, what you will get, 1 second, v input, here kp is there. Okay, this one I am bringing this side. Okay, minus is there, this will go to here, means kn into plus kn into v in, I will get. Okay, vtp, okay, sorry, kn into plus kn into vtp I will get. Okay, vtp minus kp into vdd, plus kp into vtp. Okay, here anyway one v out, which one will cancel, 1 second, 2 kp into v out, vdd. Okay, I think vdd get cancel. Here you will get 2 kp into v out, you will get 2 kp into v out, you will get. Okay, so 2 kp into v out plus v out, 2 v out, somewhere I missed, I think so, here plus will come. Okay, so minus plus vdd get cancel. Okay, so if I want to calculate a vn, what I am getting, so if I want to calculate vn, here vn equal to what, vn equal to kn into vtp minus kp into vdd plus kp into vtp plus 2 kp into v out divided by kn plus kp, okay, so where so that means if you take kp common, okay, kp common on numerator and denominator, and if you substitute, that is kr equal to what, kn by kp. Okay, kn by kp, so what equation you will get, vn equal to 2v out plus vtp minus vdd plus kn by kp is what, kr I considered, kr into vtn. Okay, kr into vtn divided by 1 plus kr. Okay, so this is the so if you substitute input voltage equal to what, VIL, this condition is what, input voltage equal to VIL, so I need to substitute, this is nothing but VIL. Okay, so VIL is, if you substitute, you will get this equation. Okay, so this is about VIL. Okay, and next if I want to calculate VIH. Okay, so what is the condition? If you calculate about VIH in this, Okay, so VIH dV out by dV in equal to -1. NMOS will be in linear region and PMOS will be in which region? Saturation region. Okay, so that condition I need to substitute and I need to calculate. Okay, so see here, so that means calculation of VIH. Calculation of VIH. Okay, so if you see calculate the VIH, dV out by dV in, that is equal to -1, and in this NMOS will be which region? Linear region, and PMOS will be which region? Saturation region. Okay, PMOS will be saturation region. So from this I can write as IDN linear equal to what? IDP saturation. IDP saturation. Okay, so just substitute that equations. Okay, linear and saturation region current equations you substitute, and here if I do what I will get? Kn by 2, 2 into VGSN minus VTN minus into VDSN minus VDSN whole square divided by 2. Okay, this is the equation in linear region. That is equal to Kp by 2. Okay, Kp by 2 VGSP minus VTP whole square. Okay, so you know that VGSN equal to what? So we already seen that VGSN equal to what? VGSN equal to Vin, and VDSN equal to what? V out, and VGSP equal to what? Vin minus VDD, and VDSP equal to what? V out minus VDD. Okay, VDSP equal to what? V out minus VDD. Okay, so this I am going to substitute. Okay, V out minus VDD. Okay, so here I am substituting Kn by 2 into Vin minus VTN minus into V out minus V out square divided by 2, that is equal to Kp by 2. This is what? Vin minus VTP whole square. Okay, just I am substituting that values. VGSN equal to Vin, VDSN equal to V out, and VGSP equal to Vin minus VDD. Okay, 1 second. VGSP equal to what? I need to substitute this one. No, okay, 1 second. Here I need to substitute what is that? VGSP equal to what? Vin minus VDD minus VTP. Okay, minus VTP I need to substitute whole square. Okay, now differentiate the above equation with respect to what? Vin. Okay, differentiate the above equation with respect to Vin. Okay, so if you differentiate this equation, okay, differentiate the above equation with respect to what? With respect to V. Okay, with respect to V. Okay, so here what I will get? With respect to V, and I am doing, no? So Kn by 2 into 2 Vn minus VTN dV out by dV in minus here what you will get? Here 1 second. V out minus okay. This is UV formula, no? So UV formula means what? UV formula means U into V minus V into U. Okay, so here what you will get? Plus here 2 V out you will get. Okay, so this is UV formula I need to apply. What? Plus 2 V out minus 2 this is x square. X square means 2x, no? 2 V out divided by so here divided by 2 is not there. Okay, just I wrote this, but divided by 2 is not there, only V out square is there. Okay, so 2 V out into dV out by dV in that is equal to Kp by 2. So here what you will get, 2 into V in minus VDD minus VTP. Okay, and differentiation of V in is nothing but 1, no? Okay, so anyway 2 get cancelled, all these things 2 get cancelled. Okay, here also 2 get cancelled, and next you substitute dV out by dV in equal to what? Minus 1. Okay, next you substitute dV in by dV out equal to minus 1. So when you substitute, what you will get, Kn, okay, here minus Vn, directly I am writing minus Vn plus VTP. Okay, this I substituted as what? Minus 1. Okay, plus V out plus V out plus V out, again here plus V out, that is equal to what I will get, here what I wrote, yes. So here what we will get, Kp into Vn minus Vdd minus VTP. Okay, so minus VTP. So here you bring this Kp and Kn on one side and remaining on another side. Okay, and you take V in common. Okay, so that means you bring this side. Okay, so what you will get, V in common, Kp plus Kn you will get. Okay, Kp plus Kn, this is equal to here what you will get, Kn into VTP plus 2 Kn into V out, plus Kp into VDD. Okay, you bring this to this side. Okay, Kp into VDD plus Kp into VTP. Okay, so that means here V in equal to what? V in equal to Kn into VTP plus 2 Kn into V out plus Kp into VDD plus Kp into VTP. Okay, VTP divided by Kp plus Kn. Okay, so what is VIH? Just substitute this Kr equal to what? Kn by Kp. Okay, Kn by Kp, and then you will get VIH. Okay, so VIH equal to what you will get? Just substitute that value and take this Kp common. Okay, so that means VIH equal to what you will get, VDD, Kp common on numerator and denominator. Okay, plus VTP. Okay, here I took Kp common in the numerator and denominator, plus here V out. So Kn by Kp equal to, I can write as what? 2 Kr V out, plus Vtn. No? So Vtn means Kp I am taking once again. Kp means Vtn you will get, Vtn. Okay, Kp VTP. Okay, Kn is there. Okay, Kn by Kp means Kr. Okay, this is Kr. Okay, Kp I am taking common, no? Kr divided by 1 plus Kr. Okay, so this is my VIH. Okay, so VIH. So if you see, like for symmetrical, so basically this problem, this formula, so it's hard to remember. Okay, hard to remember. So basically in the problems we'll use the symmetric CMOS. Okay, so for symmetric CMOS circuit. Okay, CMOS inverter. Okay, symmetric CMOS inverter, we will consider that Vtn equal to what? Vtn equal to VTP, and there is this ratio, no? What is this ratio? Kn by Kp. this is equal to kr, I will consider as 1. Okay, so if you substitute these values in the above equation, you will get VIL equal to what? 1 by 8 1 by 8 3 VDD plus 2 VTN. Okay, so this is for VIL, this is for VIL. Okay, and next for VIH, this is equal to 1 by 8 1 by 8 uh, this is 5 ADD minus 2 VTN, 2 VTN. Okay, so this is for VIH. Okay, so that means from here I can say that NMH equal to what? VDD minus VIH. Okay, and NML, noise margin low, equal to VDD minus VIH. Noise margin high equal to VDD minus VIH. Noise margin low equal to VIL. Okay, VIL. So if you see the diagram, and if you want to find out the noise margin low and noise margin high, so here you see from the inverters. So here if you see this one, okay, from the voltage transfer characteristics, so I can say that this is nothing but what? NML. This is nothing but noise margin low. Okay, so noise margin low. Okay, noise margin low, what you will get? VIL minus 0, so that is nothing but VIL. Okay, so NML equal to what? NML equal to VIL, so this is VIL only. NML equal to VIL, noise margin low equal to VIL. And NMH, okay, NMH equal to what? This value is nothing but NMH. Okay, so this is nothing but NMH, noise margin high. Okay, so noise margin high, if you see what is the difference, so that means VDD, so this is equal to what? VDD minus VIH, VDD minus VIH. Okay, so noise margin high equal to what? VDD minus VIH, VDD minus VIH. Okay, so like this you need to find out the noise margin of this noise margin low and noise margin high, and for this CMOS inverter VIH and VIL. Okay, any doubts in this derivation and all those things? Give response, yes or no, or any doubt. Shall I move forward?
Yes, sir.
Okay, next you see. So next here 1 second, please. Yeah, so if you see the CMOS characteristics, okay, so what are the characteristics of CMOS? Okay, why we are going for the CMOS in the VLSI? Okay, so there are some characteristics in the CMOS. Okay, those characteristics we'll see. Okay, so here if you see the CMOS characteristics, so it is, so means CMOS characteristics, it is having a high noise margin, it is having high noise margin. Okay, noise margin, and it is a low static power dissipation, low static power dissipation, okay, and you have high input impedance, okay, impedance, and low output impedance, okay, and next you have this is ratioless logic. Okay, this is ratioless logic. ratioless logic. Okay, so these are some characteristics of CMOS. Why we are preferring the, so there are so many logics are there, dynamic logic and NMOS logic the static CMOS logic, those are so many are there. But why we are going for CMOS logic means due to this characteristic. It is having high noise margin, low static power dissipation, high input impedance, low output impedance, and ratioless logic. Okay, and next if you see, yes, this one. So see here, so what is this noise margin? Okay, so noise margin is nothing but it explains up to what extent IC allows noise in the transmission of logic 0 and logic 1. How much of noise it can allows. Okay, IC allows, that is nothing but noise margin. Okay, so basically in digital integrated circuits we don't receive only two voltages. That means other than that we'll receive some other voltages also. Okay, so that means one for logic 0, another for logic 1. Suppose we'll receive some range of voltages that we identify as what logic 0 and logic 1. So suppose like if you consider in the in this what we call there are some so if you consider like voltage levels, so the voltage levels will be, suppose so here let us take this is 0 to 0.7 volts, 0 to 0.7 volts, so this we call as what, logic 0. Okay, and this let us take some it should cross with 3.25 volts, we'll consider as what, we'll consider as logic 1. Okay, so in this this will be like we can't consider in between these voltages. Okay, so these are the some voltage levels. Okay, so here if you see so here received voltages widens based on the noise in the circuit. Okay, so error is less transmission, noise margin is, so for less error transmission, okay, so noise margin should be more. Okay, noise margin should be more. Okay, so see here example of noise margin means, suppose three inverters are there. So three inverters, if you are like you are passing logic 0, you are getting logic 1. Okay, there will be some interconnect. Okay, and this is nothing but noise. Okay, this is nothing but noise, and here you are getting 1 and here you are getting 0. Okay, and again one more interconnect, and here you are getting 0 and here you are getting 1. So like this, so many interconnects are there in within an IC. Okay, so that means in order to get less noise, noise margin should be more in our IC. Okay, so if you see, so as I told you, like this I drawn the noise margin low and noise margin high. So that means noise margin low and noise margin high is nothing but what, this is nothing but a noise margin low. One second. Okay, so noise margin low, so this is nothing but we can call as NML, and this is nothing but NMH. Okay, so from this I can say that noise margin low equal to what, noise margin high equal to VOH minus VIH. Okay, so VOH what you got previously, you got this is VDD minus VIL, no, VDD minus previously what you got, I told you in this so here I shown with this diagram. Okay, so here NML equal to what, VDD minus VH, NMH equal to NML equal to VIL, no. So from this so VDD minus VIH. Okay, so here if you see, so this is nothing but this is VDD. Okay, this is nothing but maximum value VDD. Okay, so I can write NMH equal to VDD minus VIH, and NML equal to a noise margin low equal to so VIL minus 0 means what, you are getting VIL only, this is 0. Okay, so VIL minus VOL is anyway 0 only. Okay, so that means here if you see this voltage transfer characteristics and if you draw this waveform, okay, if you draw this so this is 0 to VL, this is nothing but what, you are applying logic 0 at input. Okay, and VIH to VDD, so this is nothing but you are applying logic 1 at input. Okay, as I told you, like VIL can be some 0.7 volts. So again VIH will start from around let us take 3.5 volts. Okay, so this is logic 1 at input, this input I am giving. Okay, and output where you are getting So that means if we are giving input, you are getting the output logic one at a VOH to VDD. So that there is a difference. Okay, this is nothing but what NMH. Okay, this difference NMH equal to what, you got VDD minus VIL. Okay, and next, if you see this one, okay, if you are applying logic 1 for the inverter, so here you are getting logic 0, that this difference is nothing but what, noise margin low. This is noise margin high and noise margin low, so this is VOL minus 0 means you are getting VOL only. Okay, VOL only. Okay, so this is noise margin based on the VTC of inverter, voltage transfer characteristics of inverter. Okay, and so what is this place? This space is nothing but what, this region. That means what, this region, VAH and VAL, this region. So we already seen this region is nothing but both NMOS and PMOS will be in which region? Saturation region, no? So in this region we already seen. So in the last class, so in this both this is unused case. Okay, unused region. Both NMOS and PMOS both will be in saturation region. Okay, this place. Okay, this place equal to what, this place. Okay, so this is about noise margin.